Welcome to this presentation on Kolmogorov-Arnold Network for machine learning-based motor condition diagnosis. This work highlights a novel architecture for an alternative or to enhance machine condition monitoring, accuracy, and interpretability. I am Eduardo Junior Piedad, and together with me, I have other authors from other institutions. This presentation, we will first introduce the context and motivation for this research. We will then discuss the dataset used, outline the novelty of the CAN architecture, which is the most recent um, model that the scientific community is currently exploring. We will also present key results in this research and conclude with the study's implications. We know that industry has a need to optimize uh, their systems to avoid in that downtime costs, and in order to be more efficient we need fault diagnosis systems. Nowadays we have AI, emerging technologies that would explore patterns and uh, features that would enhance condition monitoring. We know that conventional models have limitations such as computational complexity, fixed division functions, lack of interpretability, especially. And lastly, we are exploring the novel contribution of the recently uh, discovered or proposed model that learn spline parameterization the activation functions that would serve. So there's a need for accurate and interpretable machine fault detection systems, and we propose CAN as a superior alternative to conventional models such as ML. The data set used includes diverse fault conditions, which is common, such as the bearing axis misalignment, stutter, coil interturn short circuit, outer broken strip damage, and outer ring bearing fault. So these faults are synthetically applied, and we also compare it with a healthy or normal motor. So upon gathering data with the synthetically applied uh, 5 motors under 5 loading conditions, we perform um, the conventional uh, fast Fourier transformation to transform time series signals into Fourier transform, and then frequency domain. And then this frequency domain, we use scan to those data, and we train using this model. So CAN introduces flexibility, interpretability by replacing fixed activation functions with learned splines, paving the way for more accurate machine condition diagnosis. So imagine if you have a machine learning model and then you can uh, make, instead of fixed activation functions, you can replace it with learnable splines. So here, our initial configuration has 500 neurons with 5 output neurons. CAN's training process ensures an optimized model by refining active components for reducing complexity. So here, we train CAN with sparse regularization. We prune it to make it smaller, continue training pruned CAN, and then obtain a symbolic function. So we use the optimization limited memory VFGS optimizer, and we use 60 steps using cross entropy loss. our experiments demonstrate that CAN consistently outperforms MLP, especially in validation accuracy, making it a strong candidate for motor fault diagnosis. As you can see here, we have a higher um, accuracy um, validated using tenfold stratified cross validation. You can see also the convergence and the closed convergence of the training and testing process, giving us the hint, no, that the model does not overfit. CAN achieves 88.27% validation accuracy, outperforming uh, the previous model, the multi-layer perceptron, which is around 84.10%. CAN provides interpretability by visualizing activation splines, a significant advantage over black box models like MLP. You can see here some examples of the splines. Learnable splines converted to symbolic functions for human interpretability. This enables transparent decision making and actionable insights. CAN's performance is highly competitive, showing or showcasing its potential as a robust fault diagnosis model. So you're comparing it with other models, CAN ranks among the best performing models, surpassing most traditional ML algorithms. For more for the comparison, please refer to the paper. But here we can see that CAN performs comparably to advanced models like GBM. Like GBM in the previous literature is the best performing machine learning models, and CAN can compete with the best model available. Despite its advantages, CAN's longer training time is a challenge that warrants further optimization in future work. The longer training times compared to MLP and computationally intensive due to spline parameterization are the disadvantages of CAN over multi-layer perceptron and other machine learning models. In conclusion, CAN can achieves higher accuracy and interpretability than traditional MLP, and it has a potential to revolutionize predictive maintenance and fault diagnosis. In our future work, we will focus on refining its efficiency as well as real-world deployment. This ends my presentation. Thank you so much.